Good afternoon. Today our group will present Knowledge Graph Chapter 5, Inductive Knowledge. As we studied earlier, deductive knowledge is characterized by precise logical consequences, but inductively acquired knowledge involves generalizing patterns from a given set of input observations. It can be used to generate novel but potentially imprecise predictions. For example, as shown in the table, we may observe the pattern that almost all capital cities of countries have international airports serving them from a large data graph with geographical and flight information. So we can predict that if Santiago is capital city, it likely has an international airport serving it. However, the predictions drawn from this pattern do not hold for certain. For example, Badens, the capital city of Liechtenstein, has no international airport serving it. So prediction will often be associated with a level of confidence. For example, we may say that a capital has an international airport in 187/195 of cases, offering a confidence of 0.959 for prediction made with the pattern. Like this, we refer to knowledge acquired inductively as inductive knowledge, which includes both the model used to encode patterns as well as the prediction made by those models. The figure below is an overview of the inductive techniques typically applied to knowledge graphs. We now discuss each of the aforementioned techniques in turn. So we will proceed with the presentation in the following orders. Analytics is the process of discovering, interpreting, and communicating meaningful patterns inherent to data collection. Graph analytics is then the application of analytical process to graph data. The characteristics of the graph are suitable for certain types of analysis that draw conclusions about nodes and edges based on the topology of the graph. That is, how the nodes in the graph are connected. Graph analytics draws upon techniques from related areas, such as graph theory and network analysis, which have been used to study graphs representing social networks, the web, internet routing, transport networks, ecosystem, protein-protein interactions, linguistic co-occurrence, and more besides. On the left is a graph of protein-protein interaction, and on the right is a graph showing linguistic co-occurrence. First, we introduce the key technologies that can be applied to graph analysis. Then we discuss the framework and language that we can use to actually compute those analyses. Given that many traditional graph algorithms are defined for unlabeled graph, we then describe a way in which analytics can be applied over directed edge label graph. Finally, we discuss the potential connection between graph analytics and querying and reasoning. A wide variety of techniques can be applied for graph analytics. As our survey shows, there are major technologies such as centrality, detection, connectivity, and node vertex similarity. Centrality aims to identify the most important node or edges of a graph. Specific node centrality measures include degree, betweenness, closeness, eigenvector, page rank, hits, cost, among others. Community detection aims to identify communities in a graph. In other words, subgraphs that are more densely connected internally than to the rest of the graph. Connectivity aims to estimate how well the graph, which represents the elasticity and reachability of the graph element, is connected or unconnected. Node or vertex similarity aims to find nodes that are similar to other nodes by virtue of how they are connected within their neighborhood. Node similarity metrics may be computed using structural equivalence, random walks, diffusion, corners, and so on. For example, a node centrality measures might predict transport hubs in figure 5.2, while edge centrality might predict traffic by finding connections on which many shortest routes depend. Community detection applied to figure 5.2 may detect a community to the left, the north of Chile, to the right, the south of Chile, and perhaps also the center, Chilean cities with airports. In the context of figure 5.2, such analysis may tell us that routes to great glaciers, Osorno volcano, and Piedras Rojas, and the most brutal, becoming disconnected if one or two bus routes fails. In the context of Figure 5.2, such analysis may tell us that Calama and Arica are similar nodes based on both having return flight to Santiago and return buses to San Pedro. While the previous techniques accept a graph alone as input, other forms of graph analytics may further accept a node, a pair of nodes, and so on, along with the graph. Pathfinding aims to find paths in the graph, typically between pairs of nodes given as input. We could use such algorithm to find the shortest path in Figure 5.2 from Torres del Paine to Mumbelli. Most of the aforementioned techniques for graph analytics were originally proposed and studied for simple graph or directed graph without edge labels. Various frameworks have been proposed for large-scale graph analytics, often in distributed setting. Among these, we can mention Apache Spark, GraphLab, Pressure Signal Collect, SHA. These graph parallel frameworks apply a systolic abstraction based on a directed graph where nodes are seen as procedures that can send messages to other nodes along edges. Computation is then iterative, where in which iteration each node reads message received through inward edges, perform a computation, and then send message throughout edges based on the result. This framework then defines the systolic computational abstraction on top of the data graph being processed. Nodes and edges in the data graph become nodes and edges in the systolic graph. To take an example, assume we wish to compute the places that are most easily reached by the routes shown in the graph of Figure 5.2. A good way to measure this is using centrality, where we choose page rank, which computes the probability of a tourist randomly following the routes shown in the graph being at a particular place after a given number of hops. We can implement PageRank on large graph using a graph parallel framework. In Figure 5.3, they provide an example of an iteration of PageRank for an illustrative subgraph of Figure 5.2. The nodes are initialized with a score of 1 over 6, where we assume that the tourists to have an equal chance of starting at any points. In the message path, each node V passes a score of d times RIV over the absolute value of EV on each of its outgoing edges, where we denote by d a constant damping factor used to ensure convergence. Typically, d is 0.85, indicating the probability that a tourist randomly jumps to any place. By RIV, the score of node V, in iteration I, the probability of the tourist being at node V after I hops, and by the absolute value of EV, the number of outgoing edges of V. The aggregation phases for V then sum all incoming messages received along with its constant share of damping factors to compute Ri plus 1V. We then proceed the message path of the next iteration, continuing until some termination criterion is reached and final scores are output. An algorithm in this framework consists of the function to compute message value in the message path and accumulate the message in the aggregation path. As mentioned earlier, most of the analysis presented so far can be applied to undirected or direct graph without edge metadata. That is, edge labels are attribute value pairs in the form of native. Projection, weighting, transformation, customization strategies can be applied to make data graph subject to analytics of this form. Projection involves simply projecting an undirected or directed graph by optional selecting a subgraph from the data graph from which all edge metadata are dropped. Weighting involves converting edge metadata into numerical value according to some functions. Many of the aforementioned techniques are easily adapted to the case of weighted graph. For example, the graph of Figure 5.3 may be the result of extracting the subgraph induced by the edge labels, bus and flight from a large data graph, where the labels are then dropped to create a directed graph. We can consider the weight in the graph in Figure 5.3 which represents travel time or price, traffic, and so on, and we can calculate the shortest or weighted path considering time by adding the duration of each section of each trip. If there is no external weight, we can map edge labels to weight based on some criteria to assign the same weight to all flight edges or bus edges. Transformation involves transforming the graph to a lower IT model. The transformation may be lossy, meaning that the original graph cannot be recovered, or lossless, meaning that the original graph can be recovered. Customization involves changing the analytical procedure to incorporate edge metadata, such as was the case for pathfinding based on path expression. Other examples might include structural measures for node similarity that not only consider common neighbors, but also common neighbors connected by edges with the same label. Label or aggregate centrality measures that capture the importance of edges grouped by label. Figure 5.4 provides an example of lossy and lossless transformation from a directed edge label graph to directed graph. In the lossy transformation, B, we cannot tell if the original graph contained the edge EQQ flight Santiago or rather the edge EQQ flight Arica or both. The lossless transformation C requires the introduction of a new node similar to replication to maintain information about the edges in the specified direction. Both transformed graphs further attempt to preserve the directionality of the original graph. The results of an analytical process may change drastically depending on which of the previous strategies are chosen to prepare the graph for analysis. The choice of strategy may be non-trivial one to make priori and may require empirical validation. More study is required to more generally understand the effect of such strategies on the results of different analytical techniques over different graph models. As discussed in section 2.2, various languages for querying graph have been proposed down through the years. One may consider a variety of ways in which query language and analytics can complement each other. First, we may consider using query language to project or transform a graph suitable for a particular analytical task, such as to extract a graph of figure 5.2 from a large data graph. Query languages such as SparkQL, Cypher, and Jigwell allow for outputting graphs, where such queries can be used to select the graph for analysis. These languages can also express unlimited analytics, like non-recursive analytics, where aggregations can be used to compute degree centrality, and they may also have built-in analysis support, just as Cypher allows you to find the shortest path. In other directions, analysis can contribute to the query process in terms of optimization. For example, connection analysis might suggest a better way to distribute large data graph across multiple systems for queries, for example using minimal cuts. Analytics have also been used to rank query results over large graphs, selecting the most important results for presentation to the users. In some use cases, we may further wish to interleave querying and analytical processes. For example, from the full data graph collected by the trust board, consider an upcoming airline strike where the board wishes to find the event during the strike with venue in cities are reachable from Santiago by public transport due to the strike. Hypothetically, assuming airline information is available, query can be used to extract transport networks other than airline routes, and analysis can be used to extract strongly connected components containing Santiago. Finally, use the query to find events for cities that are not in the Santiago component on the specified date. While one could solve this task using an imperative language such as Gremlin, GraphX, or R, more declarative languages are also being explored to express such texts, with proposals including the extension of graph query languages with recursive capabilities, combining linear algebra with relational algebra, and so forth. As is studied in Chapter 4, merge graphs are often associated with the ontology that defines the meaning of semantic system or domain terms, resulting in entanglements. For example, applying an analysis with or without such entanglement, such as before or after realization, can produce fundamentally different results. For example, if the inverse axioms host of venue is called, observe that the edge Santa Lucia host EID 15 is semantically identical to edge EID 15 venue Santa Lucia. However, these edges are not equivalent in terms of analytical techniques that consider edge directions. Including one type of edge, another type, or both can have a major impact on the end result. To the best of knowledge, the combination of analytics and entanglements has not been well explored, leaving open interesting research questions. Along these lines, it may be of interest to explore semantically invariant analytics that yield the same results over semantically equivalent graph, that is, graph that entails one another, thus analyzing the semantic contents of the knowledge graph rather than simply the topological features of the data graph.
5.2 section, we will introduce some technique of the knowledge graph embeddings. There are many traditional machine learning techniques as some dense numeric input representations in the form of vectors, which is quite distinct from how graphs are usually expressed. But how can graphs or nodes and edges thereof be encoded as numeric vectors? There's one way is that using one-hot encoding, and this is the number of edge labels, and this is the number of nodes in the input graphs, and then replacing a 1 as the corresponding index to indicate the existence of the respective edge in the graph, or 0 otherwise, but typically result in large and sparse vectors, which will be detrimental for most machine learning models. And the goal of knowledge graph embedding is that create a dense representations of the graph that in a continuous no-dimensional vector space that can then be used for machine learning tasks. And the dimension always between 50 and 1000, and we use D to denote dimension. And graph embedding is composed of an entity embedding for each node. This is a vector with D dimensions, and this is a relation embedding for each edge label, typically a vector with D dimensions. And the overall goal of these vectors is to abstract and preserve latent structures in the graph. There are many ways in which this notion of an embedding can be instantiated. And then we could define the scoring function given an edge SPO, and the scoring function includes this. This is the entity embedding of node S, and this is the entity embedding of edge label P, and this is the entity embedding of node O. And then we can using this compute the plausibility of the edge, how likely it is to be true. Given a dead graph, the goal is then to compute the embedding of dimension that maximize the plausibility of positive edges and minimize the plausibility of negative examples. Typically, edge in the graph with a node or edge neighbor change such that they are no longer in the graph. According to the given scoring function, the resulting embeddings can then be seen as model named through self-supervising that encode features of the graph, mapping input edges to output plausibility scores. Embedding can then be used for a number of low-level tasks involving the nodes and edge neighbors of the graph from which they were computed. First, we can use the plausibility scoring function to assign a confidence to edges that may, for example, have been extracted from the external source. And secondly, the plausibility score function can be used to complete edges with missing nodes or edge neighbors for the purpose of link prediction. And thirdly, embedded model will typically assign a similar vector to similar nodes and similar edge neighbors, and thus they can be used as the basis of similarity measures, which may be useful for finding duplicate nodes that refer to the same entity or for the purpose of providing recommendations. There are some different models of knowledge graph. Firstly, we discuss translational models that adopt a geometric perspective whereby relation embeddings translate subject entity to object entities in the node dimension space. We then describe tensor decomposition models that extract random factors approximating the graph's structure. Thereafter, we discuss neural models that use neural networks to train embeddings that provide accurate plausibility score. Finally, we discuss language models that leverage exciting word embedding techniques, proposing way of generating graph-like analogs for their expected inputs and some environment-aware models. Discussing the tensor-based model. The basically translational model is the trans-E model, embedding entities and relations into the same node-dimensional vector space. For example, the edge neighbor path is same as the transform the San Pedro and the Mon Valley. And San Pedro and Mon Valley is the entity and the path is the relation between the two entities. And if the San Pedro plus the path that equals the Mon Valley, and then we mapping it to the two-dimensional vector space like this. And there are some other models of the translational models. And then we introduction the tensor decomposition models. Before that, we introduction the tensor. A tensor is a multi-dimensional numeric field that generated by like these zero-order tensors. And vector is the one-order tensors, and matrix is the two-order tensors. It, tensors have become a widely used abstraction for the machine learning, and then we suppose a matrix if I want to represent the color of this that is on the fifth row and third columns. To express the position of the element requires a combination of two indices 5, 3, and express the position of the element inside the third-order tensor requires a combination of three indices I, J, L, and a tensor of order D more than 3 can be understood as a D-dimensional generalization of matrix, where the order D is actually the spatial dimension, and the tensor can be considered as a multidimensional array. And then we will introduction about the canonical ploiadic. This is the decomposition of a tensor into a sum of multiplied single-rank tensors. For example, given a third-rank tensor G, and this O times is the outer product of the vectors, and R is a positive integers. And let's take it to the graph. Graph can be encoded as a one-hot three-order tensor G with three elements, where the element Gij is a set to 1 if the ith node linked to the kth node with the h having the jth label, or 0 otherwise. Letting x, y, z denotes the matrices formed by these matrices, respectively, with each vector forming a column of the corresponding matrix. We could then extract ith row of y as an embedding for the ith relation, and the jth rows of x and z as two embeddings for the jth entity. And there are some models of tensor decomposition models. And this model has some limitation of that is a previously discussed approach is that they are some either linear that preserving addition and scalar multiplication, or binary that matrix multiplication operations over embedding to compute the plausibility scores. So, for solve this limitation, a number of approaches rather use neural networks to learn embedding with non-linear scoring function for plausibility. There are some models of the neural models. And next, we're talking about language models. Embedding techniques were first explored as a way to represent natural language within machine learning frameworks. The vector-vector and glove being two similar approaches. Both approaches compute the embeddings for words based on large corpora of text such that words used in similar contexts have similar vectors. And vector-vector use neural network strength either to predict the current world from surrounding world like this model. And to predict the surrounding world given the current world like this model. And the graph rather applies a regression model over a matrix co-occurrence probabilities of word pairs. Embedding generated by both approaches are widely used in natural language processing tasks. Another approach for graph embedding is South-Dew leverage proven approaches for language embeddings. And there are some models of language models. Finally, the embeddings thus far consider the data graph alone, but what if the odd node or set of rules is provided? The entailment-aware models used constraint rules to refine the predictions made by embeddings. This model use the functional and inverse functional definitions as constraints, such that, for example, if we define that an event can have at most one value for venue, this used to lower the possibility of edges that would assign multiple venues to an event. And there are some other models of entailment-aware models. These works are interesting example of how deductive and inductive forms of knowledge, in this case rules and embeddings, can interplay and complement each other. Thank you very much.
Hello everyone, my name is Tuan. Today I will present to you the two sections, which is graph neural network and symbolic learning. The first section is graph neural network. So, first, what is a graph neural network? Unlike embedding, which aim to provide a dense numerical representation of graphs suitable for use within existing machine learning model, a graph neural network is aiming to build a custom machine learning model to adapt it for graph structure data. The structure of graph neural network is based on neural network, which the nodes in graph are neuron and the edges are weighted connection. So graph neural network is trying to build a neural network based on topology of data graph. So the graph neural network will try to learn to map input feature of node to output feature in supervised manner. Graph neural network can classify element inside graph or the whole graph itself. So there are several applications of graph network, which is node level prediction, like try to predict that this node a person in this node smoking, or edge level prediction, try to predict a link between two nodes, or the whole graph prediction. So this is the graph network structure, which consists of the input data graph that we have, consists of node and edges. Each of the nodes have their own input feature vector, which represent its own property, and the edge itself have a vector to represent it too. So we will input this data graph in a GNN structure to then output a node level embedding for each of the nodes. And so after the embedding step, we can encode this input graph data into this embedding graph data to which consists of the whole graph knowledge, which we can then use to predict some output value depend on our application. So if you are familiar with image classification tasks in machine learning, you may have heard about convolutional neural network. So the graph neural network and convolutional neural network are pretty similar. In convolutional neural network, we have kernel used to create a feature map, and each of the pixel in the feature map is calculated using its neighbor pixel value. So similar in graph neural network, we also use the information from the neighbor node to update the central node. So the task of updating node in graph neural network is called message passing. So for example, we have our input data graph right here. Let's consider updating the node 1. Node 1 have 3 neighbors, which is node 2, 3, and 4. So we will aggregate the information from these 3 nodes to update the embedding vector for the node 1. And we also do this to node 2, 3, 4, 5, and we will loop over this process several times until we want to stop it. So as you can see here, the node 1 now has gaining the information from 3 of its neighbor. We can, as I mentioned before, we can loop this process for several times. And how many times you want to process the message passing task is depend on your application. So here's an example video about message passing task. As you can see, each node will receive the information from the neighbor node to update the embedding vector. And it can loop again for many rounds. So here is the formal definition of graph neural network, which is we will have several time steps to indicate how many rounds of message passing, and the embedding vector of this node on right here in the k+1 time step will be calculated using the previous embedding vector from the k time step and the aggregate information from the 3 neighbors of it. The update function and the aggregate function can be any function like min function or max function, or we can even use a neural network to learn a function. So it will create various graph neural network variant. And after we learn the embedding vector for each node in the graph, it will depend on your application to what you will do next with the embedding vector will really depend on the application. For example, in a social network graph, if you want to recommending friend for some node, you can use the similarity between the embedding vector of nearby node. Or for example, if you want to do a classification task for node level, you may use the embedding vector of each node to and feed it into a neural network model to try to map that embedding vector to a single value that represents your label. Or also, if you want to do a whole level, whole data graph level classification, you may try to use some aggregate function for all the nodes in your graph, like for example min function, or even use another neural network to try to aggregate all the embedding vector from your other node in your data graph into a single value to serve for your application. So the next session is symbolic learning. Unlike graph neural network, which learn numerical model over graph, it's really difficult to explain or understand, or we can say the graph neural network don't provide any interpretable model to help understand why this is the case. So an alternate approach is use symbolic learning to learn hypotheses in symbolic or in logical language that can explain. For example, we can learn the rule if there is a flight from X to Y, then there also exists a flight from Y back to X. From observing that flight route tend to have a return route. Alternatively, we can learn an axiom airport. This axiom right here, which says airport are either domestic airport or international airport or even both of them. Such rule and axiom can be used for deductive reasoning and offer an interpretable model for new knowledge that is predicted. This will further offer domain experts the opportunity to verify the model because the rule and axiom can be derived by such process. Also, the rule and axiom are quantified, like as mentioned before, all flights have a return flight, or all airports are either domestic or international, so that can be applied to unseen example. So first, let's talk about rule mining. Rule mining is discovering meaningful pattern in form of rule from a set of positive edges and negative edges. The goal here is to identify new rules that entail high ratio of positive edges from other positive edges, but entail low ratio for negative edges from positive edges. Rules can be as simple as this rule right here, or can be more complex like airport near capital tend to be international airport, or even flight within the same country denote domestic flight in this rule right here. So how can we know which edges is positive and which edges is negative? There is a common heuristic called partial completeness assumption, or PCA for short, which defines the positive and negative edges like this. The set of positive edges are those already contained in the data graph, and the set of negative edges are a set of all edges that uh, if there is a edge from node X to Y prime that is not in the graph yet, but in the graph already exists a node Y such that we have a edge from X to Y. I think this is why the book is a little bit wrong. It's already in the graph. Then it will be a negative edges. Rules are not assumed to be held in all cases, but rather are associated with measure of how well they confront the positive and negative edges. We call the edges that entailed by a rule and the set of positive edges the positive entailment of that rule. So the number of entailments that are positive is called the support for the rule, while the ratio for rule entailment that are positive is called the confidence for the rule. So let's consider an example graph like this. As we can see, there is no edge from SCL to AR, but there exists a fly edge from SCL to LIM. So the SCL to AR will be a negative edge. So the support for the rule X fly to Y will we mean they also fly from Y to X is 4 because we already have ARI and fly to IQQ and vice versa, and also fly from SCL to LIM and vice versa. And the confidence of the above rule is 4 divided by 5 because the SCL fly to ARI is a negative edge. We can perform rule mining with AMIE method, which we will first starting with a rule head of the form like this, and for each such rule head, one for each edge label, 3 types of refinement are considered, and each of which add a new edge to the body of the rule. This new edge take an edge label from the graph and may otherwise use a fresh variable that not appearing previously in the rule. Existing variable that already appear in the rule or not from the graph. Here is the three refinement we may use. The first is add an edge with one existing variable and one fresh variable. For example, we can refine this rule right here by adding this left part right here, or we can refine by adding an edge with an existing variable and a graph node. For example, we can refine this above rule by giving it this part right here, or we can even add an edge with two existing variable. For example, we can keep refining this rule right here by adding this part right here. And next is axiom mining, a more general form of axiom beyond rules. It is expressed in logical language such as description logic and can be mined from knowledge graph. We can divide this approach into two, which is mining specific axiom and general axiom. To mining specific axiom, there already exists a really popular target in mining specific axiom, which is finding disjointness axiom. For example, this axiom right here states that two classes that are disjoint, meaning that the intersection of the two classes is in the empty class. Or in this specific example, no node can be simultaneously of the type domestic airport or international airport. To extract the disjointness axiom, we can find pair of classes where each has many instances in the knowledge graph, but there are relatively few or no instances of both of those classes. Or we can find pair of classes that have a cosine similarity below a fixed threshold. The cosine similarity can be computed using GF-EDF method from class vector that constructed from all other instances in the knowledge graph. For mining general axiom, given a set of positive node and negative node, the goal here is to try to find a logical class description that divides the positive and negative set. For example, given the EQ key and Arica positive set and Santiago negative set, we can learn a DL class description in this axiom right here, which denoting entities near to an airport that are not capital, of which all positive nodes are instant and no negative nodes are instant. So for simplify, that this mean if this we have three instances right here, those instances that are nearby to a airport, these two guys are nearby to an airport, but are not capital. These two guys are not capital will be in the positive set, and the one who is capital will be in the negative set. Such class description can be learned from a system like DL Learner, which is learning through a scoring function that uses count query to determine what ratio of expected edge that will be entered where the axiom is true. For example, to score this axiom right here, which means there exist nodes that receive flight from domestic airport, but that are also an international airport. We can use a graph query to count how many nodes that have incoming flight from a domestic airport. As we can see in this example graph right here, there are three of them that receive a domestic flight from a domestic airport. And we try to count how many nodes that have incoming flight from a domestic airport that and those nodes are international airport, and there is only one node right here, the SCL node, which is that have the type of international airport. And the greater the difference between these two counts, the weaker the evidence of the axiom. So in this example, the axiom has the accuracy of 1/3. So that's all we have for today. Thank you for listening. If you have any question, feel free to ask. Thank you.